Topic 4.4, Part 2, Wave Behavior Continued. Make sure you have your data booklet out so you can annotate these equations. We have the Young's double slit equation for the first one, Young's double slit equation. The S stands for fringe spacing. Lambda is the wavelength of light. Capital D, this is the distance from the slits to the screen. Distance from slits to screen. And little d is the distance between the slits. More on this later. We have the condition for constructive interference. The condition for an increase in intensity because of an overlap of waves that are totally in phase. The path difference between those waves that are meeting at some distance away must be equal to a whole integer multiple of the wavelength. When this condition is met, the waves meet in phase, like we've seen before, and you have a resulting increase in intensity. This is constructive interference. When, however, the path difference between the waves meeting at some distance is a half integer multiple of the wavelength, the waves will cancel out. So n plus 1/2 times the wavelength. More on this as we continue. Simply put, diffraction of waves is a characteristic in which waves tend to spread out through an opening, but in truth it's more complicated than that. Diffraction was first understood in the 1600s by Christopher Huygens, Dutch physicist. He stated that every point on a wave front emits a spherical wavelet of the same velocity and wavelength as the original wave. Now, wavelets aren't a complete wave. When we think of waves, we think of like an infinite series of oscillations. They spread out infinitely long in all directions. The wavelet is just a small piece of that wave that carries some of the information of the wave, but it doesn't transmit as far. So here in this animation, you see a series of wave fronts, and they're approaching an aperture, an opening here. Now what happens is all along the wave front, there are these little wavelets. That's what you see, these little disturbances, and those disturbances carry information about the wave in like a spherical wave front. And this information overlaps, some of it cancels out, but that's what transmits the information of the wave through the boundary, through the other side of the opening. This is a little far, this goes further beyond the scope of SL physics, but it's just important for you to see real wave behavior. This explains single slit diffraction, the interference pattern seen through a single slit. So as observed on the previous slide, those wave fronts were bending around the corner through the opening because of those wavelets transmitting the disturbance. The smaller the aperture, the opening B, the more pronounced the diffraction effect. So you get less of a spherical waveform through a larger opening, more pronounced and more of the spherical nature when the size of the aperture gets smaller. You can see the apertures are labeled in multiples of the wavelength. The aperture size must be of the same order of a wavelength in order for diffraction to occur. So it must be around the same magnitude as the wavelength or around there for diffraction to occur. And waves can diffract around objects, and you can image very small objects if the wavelength of the waves used to analyze the object are smaller than the object itself. So here I have a high resolution image of the coronavirus particles. They're in blue. What was used to make this image? Well, electrons. An electron microscope was used, a transmission electron microscope. Electrons have a really short wavelength, around like 50 picometers, okay, used to make this image. And the size of the wavelength of the electrons is around 50 picometers, 50 times 10 to the negative 12. The size of these virus particles is around 125 nanometers, 125 times 10 to the minus 9. So you would need some wavelength of light with this amount of energy to image the virus particles. This would be around the X-ray range. Visible light could not be used to image something this small. At 125 nanometers, X-rays can be used, but the technology has been limited because X-rays are ionizing. There's a lot of scatter. There's been difficulty in achieving the resolution with an X-ray microscope like you can with an electron microscope. But recent advances in technology mean that X-ray microscopy is likely to become more prevalent in science. Practice 1. A bat approaches an insect of wingspan length d. The bat emits a sound wave. The bat detects the insect if the sound is reflected from the insect. The insect will not be located if A. The insect's speed is less than the speed of the sound wave. No. B. The insect's wing beat frequency is greater than the frequency of the sound wave. That doesn't have anything to do with the bat being able to detect where the insect is or what it looks like. The length d is much greater than the wavelength of the sound waves, or is it d? The length d is much smaller than the wavelength of the sound waves. The bat cannot image this insect if the insect is smaller than the wavelengths of the waves. If that's the case, then the entire wave, as it gets reflected, all those wave fronts, if they're much bigger than the insect itself, you don't get a good image. The bat can't see where this little insect is. That's why the wavelets are so much smaller than the insect itself. The wavelength of the sound waves needs to be smaller than the insect for the bat to get an image based off of those reflected waves, and indeed that is the case with sound. So this animation will show two coherent wave sources, S1 and S2, coherent meaning that these waves are emitted in phase and they have the same frequency. So let's see the condition for constructive interference. So we have source 1, source 2. They're going to emit waves, and these waves are represented using these wave fronts. So the circles, wave fronts. And remember, the distance between wave fronts is a wavelength. So you can see the waves spread out, and there are places where the green and the purple circles overlap. So that is where they're interfering at those overlap positions. So let's choose a point in this interference depiction. Call it point 1, and we'll see how the waves constructively interfere at this point. They would amplify here. So the distance between S1 and P1 is labeled here, and the distance between S2 and P1 is labeled there. So let's try to do a count from S1 to P1. We'll count the number of green wave fronts we pass, and that'll be equal to the number of wavelengths. So 1, 2, 3, 4 wave fronts are counted, so that's 4 times the wavelength. And from S2 to P1, I'm counting the purple wave fronts, 1, 2, that's 2 times the wavelength. So the length between S1 and P1 is 4 times lambda, and between S2 and P1 is 2 times lambda, so this is a place of constructive interference. The path difference for the waves meeting at this position is 4 lambda minus 2 lambda. This is the path difference for the waves at P1 at this point. That is equal to 2 times lambda. Since this is a whole integer multiple of the wavelength, this is constructive interference. One more point, right here and here. This is 4 lambda, 3 lambda. So the path difference is 4 lambda minus 3 lambda for this point. 4 lambda minus 3 lambda is the path difference for this point, P2. And this is a whole integer multiple of the wavelength, so at this position, constructive interference. So destructive interference occurs when the path difference is a half integer multiple of the wavelengths. So again, our sources 1 and 2, emanating waves. Let's look what happens at this point here on the green. P2 is what I'm going to call it. We are 1, 2, 3 wavelengths from S1 to point 2. But look at from S2 to point 2. 1, 2. We haven't fully made it to the third wavefront. So that's a distance of 2.5 times the wavelength. So the path difference between them at this position, 3 lambda minus 2.5 lambda is 0.5 lambda. That is a half integer multiple of the wavelength, so this would be destructive interference. Here the waves would cancel. This spot, same thing, half integer multiple of the wavelength, the waves would cancel out destructively. Practice number 2, two loudspeakers L1 and L2 emit identical sound waves. The waves leaving L1 and L2 are in phase and are observed at points P and Q. The wavelength of the sound is 0.60 meters, that's the lambda. The distances of points P and Q from the loudspeakers are shown in the diagrams. You should be able to read this 3.10, 3.70, 3.2, 3.5. Which of the spots will have constructive interference? Which of the spots will have destructive interference? You'll get the path difference. The path difference for point P is path difference for point P or at P for these waves is equal to L2P minus L1P. And if this is a whole integer multiple of the wavelength, that's constructive interference. If it's an n plus 1/2 multiple of the wavelength, that's the destructive interference. The path at point Q, same thing, take the difference. And if the difference is a whole integer multiple of the wavelength, constructive interference. If it's a half integer multiple of the wavelength, destructive. I briefly said before, Huygens' principle states that wavelets not only allow the waves to turn corners, they also interfere with each other, which is why even through a single opening, you can have constructive and destructive interference. These wavelets spread out, carrying information, and you get an interference pattern. When light is diffracted through a circular aperture, a circular opening, an interference pattern results. Places where you have waves overlap look bright. Where they're in phase and they overlap, it looks bright. And places where the waves overlap and they're out of phase, that's destructive interference and it looks dark. And you can see like a ring-like pattern with the light waves. For SL physics, we do not focus on single slit interference. Rather, we just focus on the double slit interference pattern. So it shouldn't be too surprising that having two slits can also cause interference. You will see a pattern of high intensity and low intensity. So you have light with wavelength lambda incident on two slits, and these slits are a distance lowercase d apart. And then at some distance, capital D to the screen, you'll see an interference pattern. Bright fringes and then dark spaces in between the bright fringes. The center of the central bright pattern that's being labeled here as n equals 0, that's the central maximum, and then the subsequent bright fringes on either side of the center bright pattern, they get labeled n equals 1, n equals 2 on either side. N equals 1 would be here, n equals 2. These n's, that just means the order of the bright spot, really the positioning. And so here is the center of the slits. This has no opening, but down at the very center of the screen that the light is coming through, or that the light is incident on, this has a bright spot. This is known as the central maximum. And on either side of the central maximum, you have subsequent maxima, and then other bright spots. The distance between the central maximum and the first maximum on either side is labeled S. That's the fringe spacing. So we have this equation, that fringe spacing, that S, is equal to the wavelength of light times capital D, the distance from the slits to the screen, divided by lowercase d. We will derive this equation in class. All right, so let's look at what an interference pattern from a double slit would look like. Let's say I've taken a red laser light and clicked the red laser light on, and I pointed it at a double slit. So it's just like a black screen, but you punch two holes in it, the right size, of course, and the right spacing. And the light that gets emitted from those two openings strikes a wall, and it makes this pattern. In the middle, you see this bright spot. This is the central maximum right here, central max. It's got the highest intensity, and it's given an order. Really, it's just a position label. That's n equals 0. On either side, you have the first maxima, first max. The distance between the center of the first max and the center of the central max, this would be the fringe spacing, the S. Practice 3. Red laser light is incident on a double slit with a slit separation of 0.35 millimeters. A double slit interference pattern is observed on a screen 2.4 meters from the slits. The distance between successive maxima on the screen is 4.7 millimeters. Calculate the wavelength of light. You're going to use this equation to calculate. The slit separation of 0.35 millimeters, so that's lowercase d, and you will convert that to meters, 0.35 times 10 to the negative 3, e negative 3 meters. It says that the pattern is observed on a screen 2.4 meters away, capital D is 2.4. The distance between successive maxima, that's the fringe spacing, S is equal to 4.7 e negative 3. Solve for lambda. Calculate the wavelength. Now the question asks, how would the interference pattern change if the laser was green? Red light has a wavelength of around 700 nanometers, and the wavelength of green light is, I think it's like 550 or so, 550 nanometers. So green light has a shorter wavelength than red light. As such, I'm going to look at this equation to decide S is equal to lambda times D over little d. If I change the wavelength, how does it affect S? If I change from red to green light, I make the wavelength shorter. If this wavelength gets shorter, what happens then to the fringe spacing? Does the fringe spacing get wider, or do the fringes get closer together? Answer this. Part C of this question, how would the interference pattern change if one of the slits was covered? So for SL, this is a 1-mark question. You don't have to know anything about single slit interference to deduce the fact that if you close off one of the slits, you're letting less light through. If you let less light through, the pattern gets dimmer. There's less intensity with less light. Practice 4. Plane parallel wavefronts are incident on an obstacle. Which of the following diagrams best shows the diffraction of the waves around the obstacle? So let's get rid of choices C or D because this is diffraction. This is not refraction. The direction of the wavefronts does not change. They're not changing media here. They're just incident on a boundary or an opening. So the question then, is it A or is it B? The wave fronts, according to Huygens' wave principle, these wavelets produce these wave fronts are made up of spherical wavelets, spherical. So the edges should be rounded. Choice B. Give real-world examples of reflection, refraction, diffraction, and interference. Please note, you need to know this. These are the 4 main wave behaviors. All waves reflect, all waves refract, all waves diffract, and all waves interfere with each other. So I'm going to give an example for each of the behaviors, and then you're going to give me different examples for each of the behaviors. So I'll give 4 total, and you'll give your own 4. So for reflection, I say echo or echolocation. Sound waves reflecting off of some surface and using that to locate the object. Refraction, I'm going to say the changing direction of sound waves, changing direction of sound waves when going from warm air to cool air. Warm air is less dense, warm air is less dense and cool air is more dense. Diffraction, I'm going to say sound waves traveling out of a room. And interference, water waves overlapping offshore. Finally, practice 6. 2 identical waves leave a source in phase. Both have wavelengths of 3 meters. If they interfere with a path difference of 3/2 meters, what type of interference results? Is it constructive interference or destructive interference?